Elena Kirshanova telling us about a K-list algorithm for LW.
Thank you. Thank you for introducing me. Thank the organizers for inviting me. So originally I declared the title as K-list algorithms, but then I realized that there will be no talk that actually explains the origin of this K-list algorithm. So I would rather first tell a connection why these K-list algorithms are actually important, in particular cryptanalytic point of view. And I will present one algorithm. But I think at the end of my talk, we will actually realize that this one algorithm covers at least two knowledges. So this will be the outline of my talk. I give a definition of what I think, what I will be mentioning as a K-list problem. I will briefly introduce the LW problem, which is, I believe, known for most of the people here. And then I will describe what is known as a dihedral coset problem, which is probably known to less people. So I will focus on it for a bit more. And this part will be a bit quantum. But since we all know that we are not dummies anymore since last week, thanks to Shweta, I would assume that people are quite familiar.
Bold assumption.
Only one qubit.
2 qubits.
Oh, you got to only one qubit.
We got to 2. Yeah,
We're fine.
You get to 2. Well, once you get to 2, you're good. You can extrapolate. I will tell you how these problems are connected to each other, and based on the hardness of one problem, we can conclude something about the hardness of the other problem. So I'll start from seemingly different part, which is the K-list problem. So what is this problem about? So usually I'm giving K-lists, and without loss of generality, they will be living in n-dimensional space, and the space, let's say, in general is Rn. For our case, it will be actually discrete, of independent identical distributed elements. So this is one thing. You're given K long lists and a certain relation. And the task is to find some vectors from each of these lists that satisfy this relation. You can ask questions whether I want to find all solutions, almost all solutions, or a small fraction of its solutions. And the relation you can think about is, well, one example of a relation would be, let's take a sum of this x1 up to xk, and it should satisfy some bound, for instance. In this problem, the list will usually be the same size, and you should think about the size as being exponential in n, or maybe sub-exponential in n. And they could be as well identical. And for the problem to make sense, we should set the list size such that enough solutions exist, enough from the part that we want. If we have all solutions that we want to find all, then there should be at least one if we want to find at least one solution. I think one...
what did you say about the size of the list? So it's exponential in n?
You should keep in your head that they should be exponential in n. There will be an algorithm, there will be sub-exponential. But they're usually large. Classical example of this problem is what's called the K-XOR problem, which was introduced by Wagner and earlier, is when the lists are actually binary vectors of dimension n, and the relation, or what you want to find, is the K vectors, each one coming from each list, and the XOR is 0. And there is an algorithm due to Wagner that solves this problem in terms 2 to the square root n, having these sizes 2 to the square root n as well. For today, I will, at the end of my talk, we will develop an algorithm that is similar, but it lives in the lists are not binary vectors, but query vectors. And the relation that we want to find is that these vectors, they sum to a specific target. I put here the 0 vector, but it's any fixed vector, n over z.
Should we think of having the list as inputs, or having...
You should think of this as input.
Okay, so not like Oracle access input.
Input, really input. Yeah. The input can be large.
Yeah.
If it's input, then what about our time complexity? I mean, it's exponential size.
At least they're exponential size, and then you count the complexity as from giving you size.
Because if you have Oracle access, you have a hope to get something polynomial.
Yeah, think about this as we have actual lists. written down and given to you. And this particularly captures what's known the BKW algorithm for the learning with errors problem, which I probably will not have time to describe. But what I will be describing is this particular algorithm. Also, this particular problem captures what's known as Kuperberg's algorithm for the Dihedral coset problem. And these two problems, the DCP and LWE, are related. And my goal for the first part of the talk is to describe the relation. Now, before describing the relation, I should actually define these two problems. There are two problems that are put on my slides, LWE and DCP. So LWE, I think most of people by now describe LWE just for purposes of fixing notations. I guess otherwise it's known. My notations would be, I guess, mostly classical. So an LWE problem is defined by, or given by, three parameters. This is the dimension, the modulus, and what's called the noise rate. And for LWE, I'm asked to find a secret S, which is a n-dimensional query vector, giving m many samples of the following form. I'm giving a random vector A from ZQN, and its inner product with my secret, which is disturbed by a small Gaussian noise. So this E1, this noise, it comes from a Gaussian distribution with a standard deviation proportional to alpha Q. That's what the standard deviation, that was the discrete Gaussian looks like in one dimension. And the problem asks me to find this S. This is a purely classical problem. We know how to build crypto from it. It's important to know how hard this problem is. Typical parameters for this problem would be n choose as the bit security of your crypto system, or C total security of your crypto system. You should think about Q as being polynomial in n squared or n cubed. You should think about the number of samples being such that S is uniquely defined, and it happens whenever m is slightly bigger than n log q. And the parameter alpha, which is in between 0 and 1, is 1 over poly n, which is for proof reductions that will be square root of n over q. So it's 1 over poly n, for q being polynomial. So this is a classical problem. The problem I want to relate this LWE to is not classical, but rather quantum. So here where the qubits come. This problem has the same parameters, almost the same parameters, also the dimension and the modulus. But instead of having a noise rate, or a quantity that defines our noise, it has an integer parameter m. And what this m defines is this. So let me tell you what this extended dihedral coset problem is. It gives, instead of giving a bunch of classical samples, it gives you a bunch of quantum states. And the states, they look as follows. This is, so also, this is a quantum state not normalized. I don't normalize my quantum states throughout all my talks, so all the quantum states should be normalized as appropriate. So here, I'm giving you my S, which is shifted by the j's, and the j's vary from 0 to m minus 1, and some random vector x1. And I'm giving m of this form. So S is fixed throughout all the states. J varies for all states from 0 to m minus 1, and xi are arbitrary from zq to the n.
So should we think of the x's as being random?
You can think about x as being random.
Do we know? Are we given those also?
Sorry.
Are we given the x's also?
No, you do not know the x.
Do they have to be smaller, like they're doing?
Who? The x's?
Do they have to be small?
X's, no. X. So think about x as being uniform random from zq to the n. That would be sufficient. Sorry, what is your question?
Yeah, you just answered.
And the task is to find s. So what do we know about this problem? So first, if I give you enough m, again as an LWE, bound to n log q, then it can be shown that S is unique with high probability. What is more, maybe a more familiar notion of this problem would be to state this problem for m being 1. And for m being 1, this is what is known to people who do group theory or quantum algorithms is what's called the dihedral coset problem. So what is a dihedral coset problem? It's essentially given you, instead of m minus 1 samples, is just m equals 2. So this corresponds to this kind of samples. And also for the dihedral coset problem, we usually assume that n is 1. So it's like one
So
dimension.
the x does it have to be in the? I mean, is it quantum or classical? Because
X is, so all I give you are these quantum states. I'm not giving you anything classical.
no, when you write it here in the n equals 2 case, the x is within the bracket notation,
Correct.
but on top it's not.
I just expressed this sum. On top, it's like look at this problem as when j is when m is 1, when m is 2, it goes 0, x plus the second summand, 1, x plus s. This is precisely what this is. So just develop this sum for m equals 2, and you'll get that one. So I'm never giving you x in the clear. I'm always giving you x in the superposition. Question?
So we think of when the dihedral coset problem, we think of q as being very large, exponential.
Usually.
You don't have to.
So, like, I think morally it's right way to think when we want to keep when we want to keep the bits and the secret the same. So if you think that, like, if you want to really correspond to this problem, so here q should be q to the n rather. Is it clear so far? So just a brief remark. What is this? Why is this dihedral coset problem interesting? It emerges from the task of finding a hidden subgroup problem in non-abelian groups. So dihedral coset problem is one of the example of a group which is not abelian, but it's close to being abelian. And so a formal definition of the group, or a dihedral group, that would be the group that defines rotations and reflections of an n polygon. And this group that describes rigid rotations or reflections of an polygon is not abelian because a reflection and rotations do not compute. Okay? So if you just draw a triangle and you try to rotate and reflect, it's not the same as reflect and then rotate. And basically this S would be a hidden reflection if we phrase everything as in the problem of finding a generator of the dihedral subgroup. All right. So what do we know? So why am I introducing this problem one after the other? There is a good reason for that. So I'm just repeating the definitions just to make the comparison. It was shown that by Odette in 2002 that if you can solve the dihedral coset problem, then you can solve LWE. So this notation means precisely that from LWE samples, I can produce quantumly in polynomial time the DCP sample. So DCP is this for m equals to. Okay.
So what's the relation between the x's and the a's? Or
So I will show you similar reduction, you'll see the relation. I don't think there is too much of relation between x and a, but...
What's the relation between L and M? L is equal to M or? Okay.
That will be developed. It's a good question. You think about, at the end of the reduction, if we had m polynomial in n, then L will be also polynomial in n. But there are also restrictions on L that come not only from m, but also from your noise level. You will see that. This is actually a crucial question because the number of DCP samples will actually reflect the complexity. Well, when I write that Regev gave reduction of LWE to DCP, I should also say that LWE was not really defined in 2002, but what he showed rather is the unique SVP problem can be reduced to the DCP. But we now know that the unique shortest vector problem and LWE are essentially the question.
yeah, so when you get these independent samples on the right, should I think of them as sort of living in, a L times bigger, you know, Hilbert space that the quantum computer can act on simultaneously, or is it like a mixed state?
It's not a mixed. You're giving them one by one. You can also.
So the
They're independent.
They're independent. Yeah, that's correct.
The parameters here are not quite accurate, right? This mod q to the n, it's more like q to the n squared or something.
I'll show you q to the n reduction. Okay, okay. So you're right. So for Regef, it's indeed q to the n squared. I think if you do if you follow precisely his arguments, what I want to show you next is the question whether we can have a reverse reduction, whether we could go from whether giving an LWE oracle you can actually solve DCP. And the answer for this question is, I think, no. Well, at least we cannot show this one. What we can show is we can show a relaxed, and by we actually mean Zvika, myself, Damian, and Wei Chang, is that an equivalence can be shown not between DCP and LWE, but with an extended DCP where you have more shifts, when the M is not 2 but bigger. Okay.
What DCP Kuperman's algorithm, which is sub-exponential, why does it not give you anything reasonable for LWE?
It does. I'll show you what it gives you for LWE. That comes. That's precisely the purpose. It does give you reasonable, but it's. I will tell. So, the notion of the reasonable will develop at the end, right? All right. So, going to the question of the parameters, how the parameters between LWE and DCP change in the reduction. I'll show you the next slide, and then we go. And then I'll sketch the reduction because I think the reduction is interesting. Right. So on one hand, we have LWE samples, and we produce some EDCP samples. The parameters develop as follow. If you had an n-dimensional here, you're n-dimensional there as well. The number of the modulus remains Q and Q. There's it doesn't go anywhere. It doesn't change. The number of samples. There is an interplay between the number of samples and standard deviation of LWE and the number of resulting samples and the M. So note here that what M is, so alpha was between 0 and 1, so it kind of goes rather in the, so alpha is smaller than 1, and M, N, L, Q to the N over M are bigger than 1. So M is really kind of small, when we can say that M is poly. If alpha is poly, M, N is poly. If you want L being polynomial and Q, but if you actually plug in the parameters, M will be rather constant.
Why does, when you think that smaller noise would mean M is smaller?
So using small noise would mean M is big because alpha is the inverse of the noise rate. Right? Sorry, it's a noise rate, but the standard deviation is Q times alpha. So the smaller alpha is, small alpha is the bigger M is.
sort of, yeah, it sort of goes the opposite way I would have thought, but.
Well, think of alpha. So okay, alpha is 1 over n, versus alpha is 1 over n squared. Alpha 1 over n squared gives you smaller Gaussian, but then M is bigger because this is n squared versus n.
Okay.
Right? It's the other way. You have to inverse the alpha. So yeah, M is the inverse proportional to alpha.
How does the hardness vary in M? You know, if M is large, then it seems like you have lots of information.
Yeah. We'll go to that as well. Your intuition is correct. So if M is big, the problem becomes simple. As soon as it approaches Q and it's actually equal Q, it's polytime. When M is small, being 2 or constant, or even if it's polylog Q, we don't know how to solve it fast. In the other direction, meaning that if I want to go from EDCP part to LWE part, the picture is very similar, even actually better. We preserve the dimension, we preserve the number of samples, we preserve the modulus, and the number of shifts we have, they are inverse proportional to the standard deviation. So note here as well, if the so that's precisely what you're saying. So if there is many shifts, the standard deviations become small, so the problem becomes easier. If you have fewer shifts, the standard deviation is big, and here I'm hiding constant factors. There are constant factors everywhere. I think even here there's a square root of m needed for the number of shifts to make the reduction correct. So from 2 shifts, so okay, here we have a lower bound of m, because if m was 2, we could have done from DCP to LWE, but we are not there. So m should be at least square root m. And what I want to show you is this reduction. So this is what Odette did for unique SVP, and we can also do it for LWE in a similar way. All right. So there will be a couple of quantum steps before we arrive to EDCP sample. What do we have? So we start with LWE. So remember, I want to go from LWE samples to EDCP samples. My LWE samples, I write them as a matrix. So there will be my M samples that constitute a matrix A column-wise, and the vector B that is A as 0 plus E0. And I want to stress that S0 and E0 are my solutions. And I want to then S0 appear in the DCP sample as a sum. So what do we do first? First, we prepare a state. Again, I meet normalizations, and here you should trust me that this state can be prepared easily. First, what you do, you prepare a random superposition over J's weighted by Gaussian. Also, what I forgot to tell you is that when I defined EDCP, where was that? I could allow, so here, you could imagine that J's are weighted by uniform distribution, but they could also weighted by Gaussian distribution. And actually, in 1 dimensions, you can interplay between one another by just doing rejection sampling, and rejection sampling in dimension 1 is not possible. So J could be weighted by uniform or by Gaussian. In our case, will be weighted by Gaussian.
So the rejection sampling has to be done quantumly, not observed.
That's possible. That's possible. There exist algorithms that do rejection sampling, and they have precisely the same quality as a classical rejection sampling. All right. So we can prepare the state. Namely, we can prepare first a uniform superposition over all S's. This is a classical this quantum step, but the result is kind of known. It's easy to do. And we tensor this with some Gaussian, with the distribution over all the J's weighted by Gaussian. This is also possible to do. I will not be describing how, but you can do that. One thing to observe is that, again, as in the classical world, I can truncate my Gaussians by saying, okay, so at some point this weight for large J's is way too small, as a Gaussian would behave. So I just cut the tail of the Gaussian, and I just arrive at this nice state. Right. So this state is easy to prepare. Now I haven't used my LWE samples yet. That's a good time to use them. What I'm going to do is I'm going to apply the following function that takes as the first argument the ship J and the S that is stored here, and applies this function that depends on A, and I should put B0 here, and this should be B0. So I know these two guys. These come as the input to my function from these two states. And I put it here. Now observe what happens on this part is that I can just say that this will be my new S, which will be just A S minus G times S0. And actually,
did your state just get bigger?
Or you have like 3.
so I can assume that I have here also 0, and I can append many auxiliary. I would need 4 auxiliary registers, but I assume if you know how to manage 2 qubits, you can also manage n qubits. Yeah, so on the left, on the right part, I assume there is like zeros as many as any, but I won't need more than poly n.
Okay, that's good.
Okay, so if you just develop this, if you just look at the sum, you will see that this sum, up to permutation of summons, is the same as this one. Now I just combine as J0, I observe that there will be this S plus J0 on this part, and I just put it, and I just sort of rewrite the sum. This is the same. I just, okay, or you could say differently, I just put S prime as S plus J0. Clear? This is the same sum. Oh, now, so let's look what happens at this part. So I'm gonna make a picture of what happens on this fourth qubit. What happens on this fourth qubit is the following. So here is my state from the previous slide. And what happens is the following. So you have a sum over all s's of the points of the form as minus the error vector spread by J0. So you have a lattice point as and a cloud of errors around it. And you have this superposition over all s's. So this is one s, this is some other s, and this is over all s over zq.
Should we think of E0 as fixed, or is it?
E0 is fixed by your LW sample.
Yeah, so this, okay.
But the J, like, you know, like the J shifts this A0 in different direction, and there is like many J's. And if there is like how many J's? Well, like some J's. So there will be a cloud. But what I really want is I want the DCP sample, so I actually want this cloud. I want either this one, or any one will be good.
Elena, sorry. Can you explain the picture again? So,
All right, look at what happens on this, only on this qubit, on the last one, for a fixed S. For a fixed S, that will be AS minus sum over some J's times the fixed error. So this is my AS, and there will be many J times S around it. So think about this as a discrete set. So I mean, it's not discrete in my picture, but there will be like many points of discrete set.
but there's also the product with the S plus J.
That's correct. But I'm not looking at these coordinates. I'm looking only at these coordinates. So think about this like they live somewhere else in some other space. I'm looking currently at these coordinates. That's correct. So there will be some other space that will describe S plus J as 0, but let's not look at them. I'm going to look at these ones.
So when you visualize it as a ball, it looks more like a line.
Yeah.
Yeah, it's more like a line, indeed. But I mean,
I mean, just randomize over E0, right? Like, just
No, it's zero is fixed.
We don't want to randomize.
E0 is fixed.
So it's just the line.
E0 is fixed by LW sample.
okay.
Plus minus 2, yeah. That will be like
So the fact that E0 is small doesn't really matter here.
the what? That E0 is small, it will.
Well, because
It's
It's
Gauss,
important.
somehow the J's are going to
Oh,
be-
J is also Gaussian weighted.
J is Gaussian weighted at the beginning by my construction. So
Dimensional Gaussian.
it's a
okay.
one-dimensional Gauss, that's correct. Now the fact that E0 is small is important for the following reason. I want to sort of focus myself and I want to get one of this S. So actually I want to get this guy. And the fact that these guys are separated from each other is important. Because what I'm going to do next, I'm going to actually separate my space. I'm going to separate my space by just dividing coordinate-wise this part by, let's say, an integer d. And I choose my d such that my this kind of balls, well, we just discovered they're not balls, but actually shifts of AS, small shifts of AS, they lie in the same cube, but none of the two lie in the same cube. All right? And the important point here is that actually I have a difference between this distance, and this distance is described by the quality of my A lattice, and we know how to compute this distance, versus this distance, which is actually defined by the smallness of J and the smallness of E0. Because this radius is really the max of J times the infinity norm of E0.
So, just for some intuition, somehow we could like localize on the same S, you know, we could, but for different J's, you could somehow like subtract the states or something, or subtract the labels and get S0. Is that like?
So what I really want, I guess we want the same thing, but I'm not sure if I understood the way you phrase it. Yes, so what I want is I want to really concentrate all of this on one. And the way I'm doing it is just by separating the space.
You're going to measure which box.
And I'm going to measure the box next, precisely. So just to tell you algebraically what that would correspond to. So this separation would correspond to just look at this qubit and apply this function, and the function just divides by d coordinate-wise and takes the rounding. So that's what it does. One of my open questions would be next is how to separate this space more efficiently. The one way we could do is that what was Oda did is he put balls around each of this as minus j0. That could save a small factor of square root 10, I think. But yeah, this is what we're doing. We don't know how to do it better than this.
Elena, I think I understand how you do it, but could you go into the detail, because in that way it's not reversible. If you do it that way, your condition is not reversible, so you can't do it.
There's a measurement.
But there is a measurement. Yeah, I'm going to measure that.
Well,
You like measure the high order bit.
It's a measurement, right?
Basically, yeah, it's measuring at high order bits.
for measuring, you have to compute the value.
But you compute in a different register.
Yeah. So no, very precisely. This is So what? Yeah. Thank you. So this is like this. So what? You're right. So, but imagine that this I'm doing like on a separate register.
And then you need to delete the AS minus J.
I'll do that at the end. That I will be doing. That is correct. So thank you. This will be in separate register. So my error doesn't mean that I actually transform. My error doesn't mean I transform this state, but it rather means I add another registers and write the result on the other registers. So that's what I'm going to do. I'm going to do this boxing. We call it box, put it inside the box and measure the box. And upon measuring the box, I hope that for a fixed S, for a random S, like for an S that actually defined a point, and all the points like were the same as soon as the measurement is concerned, what I'm getting is this. And it's almost as good as DCP, except I need to uncompute this guy, but I can, so this is precisely that was the question, do I compute? I can uncompute this by applying this function. So if you do, it's actually very easy to verify that if you, on this register, apply this function, J, S, and B, this is the first input, this is the first input, the second, and the third, what you will get is actually 0 on this register. So you can uncompute that. And what you end up having is this DCP state. So going back to the question how A and S are related, well, S was like, they're not very much related, but A was random, uniform random from the Q, and S is as well. S just defines your box.
So
It comes from the same.
where did E0 disappear?
E0 I uncomputed.
Oh, into B0. Okay.
Yes, E0 was here. If you just B0 is A as 0 plus E0. That's where it disappeared.
When you measure the last register, do you not, so you're using the assumption that things are well separated to say that you only get one S?
Correct, I'm using this assumption.
Okay.
And this assumption relies on the fact that I have a gap between my error length and the lambda 1 of my lattice.
Okay.
This is precisely what I'm relying on. And I cannot, question?
Sorry, go ahead, and then I'll ask.
And I cannot, so this basically determines the number of samples I can get. I cannot measure constantly because I have only, the number of time I can measure is really defined by the difference between the error and lambda 1. Because at some point I will get like bad states. Or like states that actually, like on my picture for instance, this could be like also like a bad guy. That's kind of not in the box.
So you're saying if M gets too big, then these things will overlap, and then that's the number of ECP samples?
Correct. Correct. Well, I could, for instance, here, right? So if I took J very small, so J is under my control, the number of shifts I can do. So if I could take J very small, that would be like even shorter, and I could allow for more samples. Well, if I say, okay, I can go for big J, really, then this ball would be bigger, but then it may well intersect with another ball. So there is a really difference between the number of measurements I can do, which is defined by the quantity, how much this is smaller than this, by the number of J's.
Where did you use the Gaussian?
So actually I'm using the Gaussian just to bound this value.
I see. But like,
So, but you could start with the uniform and that would be the same, like bounded uniform.
So suppose you could prepare this state with not Gaussian but uniform distribution over the J's, which you can't here. Then you're good. I mean, then you can do Kuperberg and you get algorithm for
Well, but look, even if I take J being uniform, let's say,
over the space, over the cube.
yeah, but I still have a mass from E0, right? E0 comes from my LWE. So E0 is not 1. E0 is, let's say, square root n.
but it's fixed,
No, I understand,
right?
but so your final state is the sum of Gaussian J S plus J is 0, right? Yeah, is it?
The big problem is if your box does not contain the full.
No, I understand. But I'm saying magically, if you could get to the end of this, so the issue is that you can only get a superposition over a small number of J's as opposed to all the J's. That's the yes?
Yeah, I would like to have J's like up to Q. That would be fantastic. Yeah, but I cannot have it. Like, I mean, I will overlap. Okay, cool. So that what we got. The question is, how hard EDCP is this? This is like a good transition to this question. So this is my EDCP sample. Again, I went from Gaussians to uniform. It doesn't really matter much for the hardness, and that depends on M. So let me tell you why. So these usual things we're doing with the. So I'm already. It's like a step 0 in Kuperberg's algorithm, or an algorithm that actually solved the hidden subgroup problem, is to do a quantum Fourier transform over ZQ to the n. And the quantum Fourier transform over ZQ to the n will give us this state. Quantum Fourier transform over this is just the inner product over all y's of what was here with the y. Now that the x is the same for all j's, so I could just, first I measure y. I would measure y from this state, and I would get a random y and whatever remains for this y, which is this one. And now that because x is fixed for all the j's, I could just describe this inner product as x inner product y plus js inner product y, and the inner product between x and y is the same for all the j's, so it goes into the global phase. So it doesn't matter. So with this state, it's actually not very hard to see that this is our state and a classical y. Then if M was Q, so if we were allowed to actually make that many shifts as Q, then this state is nothing else but the quantum Fourier transform with the inner product of our secret with a random y. Right? But that means that we can have a poly n algorithm if we have poly n samples with M as large as Q. We cannot have that. If we allow M being slightly smaller than Q and N is small, then it's still easy. And this is a Childs-Van Dam algorithm. And this is an interesting algorithm because essentially what the underlying task of this problem is solving cis. But it wasn't formulated as cis, but it's actually a short integer solution in a box, and you need to find all of them. That's what it corresponds to. Now, for our purposes and for purposes of the reduction you've just seen, the M was actually small or even a constant. And in this case, where M is small, and this is the case of where we live, we have one algorithm, which is Kuperberg's algorithm, and there are two versions of it, Kuperberg in 2005 and 2011. And the 2011 was a strict improvement over 2005. So I'm going to briefly describe this algorithm.
I'm actually a bit confused as to what is this setup that, so after we've done all this, we now have this
We now have these states, and we have poly many of the states, let's say, or M, or like L states, which is.
So morally, these encode sort of random inner products with the secret with the vector y, right? With random vectors y.
Yep.
So this is, yeah.
Ah, okay, and this is, I see, so there's no error anymore.
There is no error anymore.
That's why, okay, yes.
You get- you get-
Why did we make any improvement over, you
So
know?
yeah, you get poly n of them when you just invert the matrix y.
Yeah,
Why you
yeah,
know
yeah.
classically?
Okay, gotcha. Makes sense. Yeah.
Okay, so let's go to Kuiperberg algorithm, and this will be the algorithm that, because we have a reduction from LWE to EDCP, this algorithm is also applicable to LWE. How does it work? So let's maybe be not that ambitious and try to find only the first coordinate of S, but the second, and all the other coordinates will be found in a similar way. I just want to target this one. Imagine that we had y, that we measured our y, that was of this shape. M, and all the others were Q. In this case, if you take the inner product of S, of your secret with this y, what you will get here is, so the y is Q, 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 so that cancels with the Q. And I think I should have written not M, but, let's see what cancels. That should be Q over, M over Q, that's correct. That should be M over Q, so sorry. This should be M over Q. So in that case, this inner product will give you this. And this is again nothing else but the QFT of S1.
But assuming M is big enough or something?
Um,
Doesn't M have to be Q? Like I'm confused.
no, but I mean, look, here you have just the sum of J from 0 to M, and here you have M. And you just take a QFT over that M.
Ah,
Right?
oh, okay.
And what you get is this S1 mod M.
Wait, but isn't it really M over Q, not?
M over Q, M over Q. There's a typo. It's M over Q.
Okay, but then I'm confused about what the Fourier transform is over.
Is that M? So you get the J's from 0 to M minus 1, and this is nothing else but the QFT of S1 mod M.
Okay.
So even if your S1 is over that Q, you just get shifts. You get these multiples. And once applying to QFT of this transform, you get S1 mod M. The problem is that such Y will appear with probability 1 over Q to the N. So it's unlikely that we'll get this particular Y, although it's good. But what we try to do is we try to actually get to this Y by combining several samples. And this is what Kuiperberg's algorithm is doing. So let me just tell you what the combination is and what the steps are. The question, yes?
The first coordinate here, is it M or Q?
M over Q over M. There is a typo. Q over S. So the first coordinate is Q over M. Yes? Sorry.
But why should Q be divisible by M?
If it's not divisible, it will be close to the state. I mean, there is no something that should be divisible by M. This is indeed true, but I think if it's not a very big deal to get to the state that is close to this one. So you get some. So you in that case, we'll measure the air-to distance between the Q over M and whatever the multiple is. So usually we can assume, okay, what I'm kind of hiding is the shape of Q. But since we're coming from LWE, the Q for LWE and the Q for LW and Q here are the same. For LWE, we have flexibility in Q. We can reduce LWE with one Q to LWE with another Q. So for this particular reason, I'm not super concerned about the specific shape of Q. So I'm usually like, I'm choose Q as in what I want, like the one that is comfortable for the algorithm. Okay. So here is the assumption of Q. So for the purpose of my description, I want Q being power of 2, although it's not necessary really. And the idea to get this good Y, and Y again is not M but Q over M, is to combine several states of the form that I showed. So I'm going to develop this on the board, which I think is going to be fast. So this is what I'm going to do. I'm going to show you how to go from a not so good y, a not so good state, to a little bit better state, and then we repeat these steps. So let's assume we had two states, which was from 0 m minus 1. Y and j, I call it j1, y1, and j1. And we had y1 classically, and the second one. There is a phase S y2 over q j2. Let me combine this. To stay quantumly, what I mean combine this, I mean take a tensor product. So this is how you went from 1 qubit to 2. I'm doing the same. And this is omega of what? Of j1 sy1 plus j2 sy2 over q j1 comma j2. If we have 1 qubit, we have 2 qubits. Let me rewrite this sum. This not the sum, but this fraction, this value would be omega of the inner product between S and J1 times Y1 plus J2 times Y2. J1, J2. Now this value I actually can control. Oops. I'm going to show you how to control this value because I know J1 and J2 on the superposition here, they are my qubits, and I know Y1 and Y2 classically. These values I know classically. So what I'm going to do now is I'm going to say, I'm going to find and compile all this Y1, Y2, and J1 and J2 such that on the last coordinate, so this is a vector, on the last coordinate, this is divisible by 2. I'm choosing 2 pretty much randomly. You can say if it's divisible by 4, by 8, or by whatever number you want, or by any multiple of q, but I assume that q is a power of 2. So how I'm going to do that? I'm going to define my state. So I'm going to do the following thing. J1, J2 from 0, n minus 1. The same state, the same phase here. But on this register, I want to compute y1 times j1. So yy I know classically, j1 I take from here, plus y2 times j2. Again, this is known classically, this is written here. And I take, let's say, the nth coordinates. So this is a vector. Mod 2. Okay. What I'm going to do now, I'm going to measure this last qubit. And I'm going to get some C, which will be just in B. Let's call it B, which is B either 0 or 1. But the point is that on this part, I'm going to get all the J1 and all the J2 such that Y1 times J1 plus Y2 times J2 is congruent to B mod 2. What I'm going to have here is the following. This is, so nothing changes for the first n minus 1 bits. So let me rewrite this as Si times Y1 J1 plus Y2 J2 I, where I goes from 1 to n minus 1. So all the bits, all the first n bits I keep divided by q. And the last one, I would rather rewrite as follows. So this guy, so this here, I know that these guys are all B mod 2, meaning that they have that they're divisible by, that minus B is divisible by 2. So what I'm going to write, I think I have a nice way to write it here. Okay, that will be Sn times y1 j1 plus y2 j2 over q. But this thing, as I just said, is Sn times b over q plus something that is a multiple of 2 times something that depends on a and j, or j1 and j2, sorry, and 2. And there's j1. Did those people know? So let me repeat once again. What I want just to say is I just want to separate. I just want to get closer to my vector q here by sort of reducing, by sort of pulling out the powers of 2 here. And this way, I'm going to say the following. So this one is divisible, so 2 divides q. So this one I've got here, which is a multiple of 2. Some multiple of 2 on the last coordinate. And this guy, Sn times the b, which is what I measured, over q is independent of I and j, so this goes to the global phase. So what effectively I've done is I got closer to q by a factor of 2 on the last coordinate. Okay. Okay, let me rewrite the state. So what we've got here is a state which is j1, j2, such that y1 times j1 plus y2 times j2 are b mod 2. A state here which is the same as in the previous, except I remove the S1 times b over q because it is the same for all j1, j2. j1 and j2. And the b I cannot compute because I know it, I've measured it. I'm going to write it. So the hard part of this algorithm is not really this. You just got by measurement, you just got closer to q by a factor of 2. The hard part is to actually get this j1, j2, because now you don't know them. So you cannot describe the state at the moment. Now you don't know which j1 and j2 live here. And this is where the k-list come from, and you actually do brute force. So at this stage, to actually get to know j1 and j2, what you're doing is you're constructing the list L of all vectors y1, j1, where j1 ranges from 0 to n minus 1, and L2 that depends on y2 and j2, and you combine them in the other list that contains those pairs of indices, or you could also store the indices, but here you could also say I'm storing j1 and j2. But here you just say, okay, I'm going to find all this j1 and j2. That gave me these vectors on the nth coordinates. So this is where you use like any algorithm, any good algorithm, you know how from the two lists, which you can create yourself by just y1, y2 you know, g1, g2 you know, or you know the ranges of this of this indices, and also you know what the target should be. And the time for that is the time of the two-list algorithm to find this list. So the parameters you should choose, namely this mod 2, that was more pretty much arbitrary. It's kind of not really arbitrary because you also want to say that this list is not empty. So what you do next is you figured out these indices, and you basically construct a state which becomes closer to Q on the last coordinate by a factor of 2, and then you repeat, but then you become closer to the last coordinate by the factor of 4, by the factor of 8, until you get to Q. And then you go to another coordinate n minus 1. And then you go to coordinate n minus 2 up until the end. So eventually what you end up having is a K-tree algorithm where this one was your L1, L2 to get closer to the first by a factor of 2 on the last coordinate. Then you try to combine those. So let's say we've got 2. Like this will kill the power, reduced by a factor of 2. By 2. You'll get some other fresh states. On this case, you reduce mod 4, and so on and so forth until you reduce up to mod n to, I think it will be square root n log Q. So this is the strategy.
So what's happening classically versus quantumly here? Like I'm getting confused.
So this is all classical computations you're doing.
So what did you use? I mean, where are we using quantum instead?
So quantumly, the only thing you're using is you're measuring this state B, like there you measure the most. So you're kind of measuring what's happening here, but the result of the measuring doesn't really matter much. The only thing, after you've measured the state, you've got that, but you don't know the state. The state you kind of create. You try to recreate the state classically by figuring out what this G1 and G2 are.
So the only interesting thing is sort of the probability of, from the measurement perspective, it's just the probability of getting B equals 1 or B equals 0.
Yeah, so these probabilities are usually they're like 1/2 in our case, right, more or less.
Yeah, so I'm still confused. Why can you just do this whole thing classically? Where did?
I mean, I'm giving you quantum data, right? What do you want to do? What do you want to do? What do you want to do classically here? I'm not sure that that's. The first part is indeed classical. This is this part. Is to actually get the correct state, the state that you've got after the measurement. To describe the state after you've gotten after the measurement. What you're doing is you're combining sort of, or trying to create good states out of the bad states. And the mechanics are quantum. Is that?
Yeah, maybe. I guess I'm just too confused to make sense of it. But
Okay. So it turns out that the strategy I just described, just do the first 1 bit, 2 bit, 4 bit, and so on, is, so this is what I just described. If you develop this algorithm and a strategy of the zeroizing I bits on the I step, that gives you precisely the what was mentioned previously, square root to an algorithm, but in our case, because there is Q to the n but not 2 to the n, that gives us an algorithm which is classical time and memory to the square root n log Q, and it requires the same number of original samples, original BCP samples. Because if you actually start, so that if you ask yourself how many samples do I need originally to actually, by following the strategy to get to the target, to the good state with the target y, you end up with this number. Any other question?
Yeah, one question. When you say quantum memory is small, you still have to hold the sample somewhere, and they are quantum.
One by one. one by one. So I never have to store at once many samples. I do need them, but one by one. So I really don't have to store like simultaneously. That's correct. I can do this on the fly. So once I need them, I have them. Or I can create them.
So
Next question.
I just want to view this as an attack on LWE. Okay.
If you want to view it as an attack on LWE, in general, if L samples are given, so here I described like sort of an optimal solution. You have many samples, and this would be the optimal time. If you don't have that much samples, you still can do that, but the strategy would change in the case that you do not do mod 2 or mod 4, but you combine many at once and do big chunks, and do like, and try to merge them on more bits at once than 2, 4, 8, and so on. This should remind you of the BQW algorithm. This is precisely what it does. In the case where we have only poly n many samples, we would have to sort of kill at once n over log q bits. Right, so if you put here poly n, you would get something that is exponential in n, and the multiple in front would be log q divided by log n. So log q divided, not log n, log L. So we just saw that the number of samples L is less than q, so the constant is not good. And this is what I mean by inferior to lattice attacks. However, one good point about this algorithm is that it mimics BQW classically, but it doesn't require many LW samples. We could do this with only LW samples. And it does not require large QRAM. I mean, we do need many, actually, even for LW, we don't need quantum memory is poly n. Like, we don't get many samples. So in the regime or in the world where we have, where the quantum memory is expensive, but classical time and classical memory are not, that would be kind of the best solution, because best solution up to what we know now. So what we know now is either super exponential and polynomial space, or single exponential, but then the memory is also exponential and quantum memory as well. What this strategy would allow you to do is a strategy would allow, okay, I'm still single exponential, maybe with a worst constant, but my quantum memory is only polynomial. So in the world where polynomial memory would be, where the quantum memory would be expensive, this could be an optimal. That could be an optimal algorithm. The question is.
Exponential classical memory, right?
But that's exponential classical memory. That's correct.
Then isn't classical sieving an algorithm that outperforms this? It needs even less quantum memory.
So that's that could be the case, but probably the constant would be worse for the constants would be worse for this algorithm, I guess.
So probably the same question, related question. In what regimes does it beat a purely classical?
In none.
Okay.
As far as I can see from the constant in none of the regimes. Although, yeah.
It feels kind of like Aurora good, right? In the sense that you need tons of samples, but I guess that's in like the wrong regime. It's like in the EDCP.
What do you mean by it needs tons of samples?
So in the
optimal, yes.
Yeah.
And if you don't have enough samples, you have to do more work. I think I'm largely over time, so this will be my last slide. This is just a takeoff that Copyworks algorithm is really a quantum analog of BQW. This is like a good way to view it, I think. It does not require many samples, but it's a good thing. Although a bad thing is at the moment is not better than the lattice-based attacks. Although probably this algorithm, I don't know, maybe there are ways to improve this algorithm or improve the constant. And if one can improve the constant, that would be good. And I leave two open questions, interesting or not. One of the things that the number of samples, the quality of this algorithm relies on the number of samples we have. And the question is whether there is a better space separation than the one I showed you with the cubes, with the boxes. Maybe there is a better, not necessarily efficient way to do the separation. I mean, I can also pay some time to actually do the separation. And if we actually have if we do the analog in the head with the BKW with the classical algorithm for AWE, they seem to perform better if the secret is binary or sparse or ternary. It's not really visible here. So I could not make use of the fact that the binary S for these algorithms. So this is really like, classically it seems to help, quantumly it doesn't. So with this open questions, I thank you.
Let's use lunch for more questions. I think we resume at 1:45 for the next afternoon session.